So in this part 5, we are solving past paper questions, okay? So in this question in particular, they are asking about emission spectrum. One thing, if you haven't subscribed, please subscribe and give the like button. I will creating more videos like this one that can be very beneficial for your revision and your study of the subject. Here we have that this typical question from the IP from the past paper, and this is which electron transitions correspond to the red line in the hydrogen line spectrum. So here we have the diagram, and here we have the option A, B, C, and D. So first, we know that in the visible spectrum, they are talking about a red line, meaning that is the visible spectrum. Remember that here we have the energy levels 1, 2, 3, 4, 7, and with this A is showing that the electron is falling down from an energy level 3 to energy level 2. This B is falling down from energy level 7 to energy level 2. C is going up from 2 to 3, is getting excited. And then we have that energy level 2 and energy 1 to D. This is how we read this diagram. Now, if you remember the visible spectrum for hydrogen, which is the red line, is only the one that is falling down to 2. So in that case, we don't use D and we don't use C. Now, between A and B, we need to remember the relationship between the wavelength and the energy. So if you compare the waveline, it will be a bigger wavelength. But if this is a bigger wavelength from hydrogen, it means that the energy will be the lower. So remember that the energy is inversely proportional to the wavelength. In that case, we disregard B and the correct answer will be A. So now, when an electron is falling down from energy level 3 to energy level 2, means that emission will be a red. Okay, so this is the first exercise. Here we have the mark scheme. The second exercise is this one. How are the lines of emission spectrum? Again, emission spectrum of hydrogen. It says electrons move higher energy level absorbing photons. Yes, this is true, but in that case, is not the emission spectrum. In that case, we are talking about absorbing. So that's why we say that this is not correct. Then electrons move to a lower energy levels releasing photons. This is correct. This is how electrons are moving in order to release energy or release photons. Let's continue reading the other ones just to be sure. Electrons move to higher energy levels releasing photons. This is not true whatsoever, because when electrons are increasing energy levels, it's because they've been excited. And the last one, electrons move to lower energy levels absorbing photons. So no, when electrons are absorbing photons, electrons are being excited and they jump energy level. So this is not true, and the only option will be B. And we have B. Now we have this equation. I already wrote down how to solve this question, but I will explain it step by step what did I do. This is very common, especially for higher level. Sometimes they ask about energy, wavelength, and these are the typical exercise that they are asking about this shell part. It says, when chlorine emission spectrum is produced, okay, so we need to have this in mind, there is a strong line and 453 nanometers wavelength. Determine the energy, I will highlight this in green, energy of the photon of light emitted in joules using sections 1 and 2 of the data booklet. Section 1 and section 2 of the data booklet, I provide in the following equations. First one, the one that is speed of light is equals frequency times wavelength. Then energy equals Planck's constant and frequency. We need to know that the speed of light is 3 times 10 to the power of 8. This is provided in the data booklet in section 2. Then we have the Planck constant is 6.63 times 10 to the power of negative 34 joules times seconds. And it's important that you also know that 1 mole is 6.02 times 10 to the power 23 atoms or molecules or ions. This is Avogadro's number. So if they are asking about energy and you have the wavelength, you need to make certain things first. So I will use this equation and I will use this equation. So this is the original equation. This is how I rearrange the equation in order to get the frequency. But first, the wavelength provided is in nanometers because we later need to use the speed of light, which is in meters over seconds, I need to transfer the nanometers to meters. So I am using this conversion factor here in order to change 453 nanometers to meters. Remembering that 1 nanometer equals 1 times 10 to the power of negative 9 meters. This is something that you need to know and you need to practice. The answer will be 4.53 times 10 to the power of negative 7 meters. Once I have the wavelength in meters, it's now time to use this equation because they are asking for the energy. So if I have the frequency, will be a speed of light over the wavelength that I have here in order to get the frequency. And if I have the frequency, then I will have the energy. Okay, so a speed of light here divided by the frequency that I obtained here in meters will give me 1.62 times 10 to the power of 14 hertz, which means 1 over seconds. It's exactly the same of saying 1 over seconds because that's the unit of frequency we studied in the previous parts of this series. Now, using the equation of energy equals Planck constant times frequency, we have that Planck's constant is 6.63 times 10 to the power of 34. Remember that this number is provided in the data booklet, and this is the 6.62 is the frequency that we find out before, 1 over seconds, which is the same as hertz. If you multiply this, you will have seconds go and the unit will be joules. And this, after the multiplication, will be the energy. Okay, so this is how we solve this exercise. Sometimes they are asking about a wavelength, and then you need to start from the energy. But if you start from the energy, you just need to find the frequency, then the wavelength. It's not difficult. This is another exercise, and this is how the past paper, the mark scheme is showing it. So first, you need to know how did you get the hertz or the frequency. This is something that we found here, the frequency. And then you need to show joule for 39. And here we have 439 times 10 to the power of 19, as we have here. So we made it correct. Follow this example, and then you will solve all of these kind of exercises. Here we have more questions for you. We have are taken from Pearson IB. So you can solve them. And here we have the reference for the video. Guys, if you have any particular question on your handouts about how to solve or get more of this kind of exercise or how to approach different questions, just please let me know in the comments and stay tuned. Have a good one. See you.